Let's take a look at how to simplify radicals. First off, let's look at what some examples of radicals. That's a radical there, and this is another radical. So this one here doesn't have a number in a little slot, but this does have a number in a slot. That number in a slot is called your index. A lot of definitions in math aren't that important. This one is kind of important. You have to know what your index is. Now, if you don't have a number here, like this one's blank, then by default your index is equal to 2. Now, this right here has a special name. When you don't have a number in the slot, it's called a square root. And like we indicate, that's the index of 2. If you have a number in a slot like here and it's a 3, this is called a cube root. Then after that, they'll go by the number. If this is the 4th root here, if there's a 5 here, it'd be the 5th root, and so forth. These two kind of have their own special names. Now we're going to take a look at how to simplify these. So let's take a look at our first problem and see how the index helps us figure out how to simplify. So we got square root of 24. Now remember, for our primes are 2, 3, 5, 7, maybe 11. This probably accounts for 90%, maybe 90% of what you see in college algebra. Now, there, of course, there's an infinite number of primes, but most of the problems revolve around these numbers right here. So, okay, we want to simplify the square root of 24. We want to get the prime factorization of 24. And we'll take a look at a factor tree to do that. I start with my first prime, the 2. And I ask myself if it's divisible by 2, and it is. I can rewrite 24 as 2 times 12. So 2 is prime, so we circle it. Then I keep working with the 12. I'm still on the first prime, 2. It is divisible by 2. 2 times 6. 2 is prime, so we circle it. Then on to 6. Still on the first prime. It's divisible by 2. 2 times 3. And both 2 and 3 are prime, so I circle them. Which means the square root of 24 is 3 2's and 1 3. Now this is a square root. The number in the little slot right here, it's implied 2. Since it's a 2, that means we're looking for a pair of somethings. We need 2 of whatever. Well, here's a pair of 2's. Those pair of 2's are going to come out in front as a single 2. Now we're left with 2 times 3 inside, which gives us 6. We can't bring those out because there's not a pair of them. So our answer to this problem is 2 square root of 6. Let's take a look at this. Square root of 90. And again, I'm going to do the factor tree on each one of these. A lot of you don't need to see the factor tree, but for those that do, it's here. Again, I'll start with my first prime, which is 2. It's divisible by 2. I can rewrite 90 as 2 times 45. Now, if you're wondering, well, how do you determine if it's divisible by it? Plug in your calculator. If you do 90 divided by 2, it'll give you 45. If it gives you decimals, it doesn't divide into it evenly. Now, I'm still on my first prime, which is 2. This is not divisible by 2. So I'll go to my next prime, which is 3. It is divisible by 3. 3 times 15. 3 is prime, so I circle it. I'm still on my 3. This is also divisible by 3. 3 times 5. So we can rewrite this as 2 times 3 times 3 times 5. Now our index is 2. It's a square root again, which means we're looking for a pair of somethings. Here's a pair of 3's. A pair of 3's is going to come out in front as a single 3. And we're left with 2 times 5 inside, which gives us 10. So 3 square root of 10 is our answer. Let me start a new page. Let's look at this one. We got the cube root of 27. Well, remember our primes. 2, 3, 5, 7, maybe 11. We haven't even got to 7 on these problems yet. So do the factor tree on it. 27, it's not divisible by 2, but I go to my next prime, 3. It is divisible by 3. 3 times 9. Some people do factor trees differently. They just ask you to think, well, what two numbers multiply together give you this? And I like to approach it from a more systematic approach. I like to go from our first prime to our second to our third, and so on. Well, we're still on the 3. It is divisible by 3. 3 times 3. So I see that 27 I can rewrite as 3 times 3 times 3. Now our index is 3, which means we're looking for a set of 3 of something. Well, we actually have 3 3s. So 3 3 is going to come out in front as a single 3. And since everything disappeared underneath our radical, the radical's gone. And that's our answer. Now these don't have to be 3s. We just need 3 of anything. 3 4s, 3 5s, 3 whatevers. Let's take a look at this one. We got the cube root of -8. Well, to begin with, if I just think about 8 alone, if I do the factor tree, first prime is 2. It's divisible by 2. 2 times 4. 2's prime, so we circle it. I go to 4. 4 is divisible by 2 also. 2 times 2. So it appears 8 is 2 times 2 times 2. Now with the negative in there, we could rewrite this as -2 times -2 times -2. Because a negative times a negative is positive, times another negative is negative. Now our index is 3. It means we're looking for a set of 3 of something. Well, I have 3 -2's. So those 3 -2's are going to come out in front as a single -2. And everything disappeared from underneath our radicals, so it's gone. So -2 is our answer. Now an alternative way you could have done that problem is whenever your index is odd and you have a negative inside, you can just immediately take that negative and put it on the outside. So before I begin, I put negative on the outside, and then I got just the cube root of 8. And then 8 is 2 times 2 times 2 from our factor tree. We're looking for a set of 3 of something. Here's 3 2's, so those 3 2's will come out in front as a single 2. Negative is just carrying down, and there's our single 2. And you see it gives us the same answer. Let's take a look at this example. We got 27 over 64. Sometimes, by using a factor tree, it makes it a little bit harder if we can just see what they're multiplied together. Like here, the index is 3, so we're looking for a set of 3 of something. Well, 27 is 3 times 3 times 3. Now 64, that would be 4 times 4 times 4. This problem becomes a lot harder if you try to do the true prime factorization of 64. So if you can see it, then go ahead and just write it down like this. Well, our index is 3. We're looking for a set of 3 of something. So here's 3 3/4. They're going to come out in front as a single 3/4. And that's our answer. Let me start a new page here. And time for my tablet to blow up, so let me bring up a new version. There we go. And we got square root of 48. Okay, let's do the prime factorization. We're on our first prime, which is 2. It is divisible by 2. 2 times 24. 2's prime, so we circle it. I'm still on my first prime, which is 2. 24 is divisible by 2. 2 times 12. 2's prime, so we circle it. Still on my first prime, 2. It's also divisible by 2. 2 times 6. 2's prime, so we circle it. And 6 is divisible by 2. 2 times 3. And both those are primes, so we circle them. So we got 4 2's and 1 3. So 1, 2, 3, 4, and 1 3. Now this is the square root. There is no number in this slot right here, so by default our index is 2, which means looking for a pair of somethings. Well, here's a pair of 2's. Those pair of 2's are going to come out in front as a single 2. And here's a pair of 2's. Those are going to come out in front as a single 2. Now they come out with multiplication between them, so that'll be 2 times 2 out in front, and then we're left with a single 3 inside. 2 times 2 is 4, so we get 4. Square root of 3 is our answer. You can only bring them out if you got a pair of them. We don't have a pair of 3s. Let's take a look at this one. Got the 4th root of 80. If I do the prime factorization, start with 2. It's divisible by 2. 2 times 40. 2 is prime, so we circle it. 40. 40 is 2 times 20. 2 is prime, so we circle it. 20 is 2 times 10. 2 is prime, so we circle it. And 10 is 2 times 5. And both 2 and 5 are prime, so we circle them. So we got the 4th root, and we got 4 2's, and we got 1 5. Our index, the number in the slot right here, is 4, which means we're looking for a set of 4 of something, which works out nice because we've got 4 2's. So those 4 2's are going to come out in front as a single 2. And the 5 remains inside. We can only bring it out if we got 4 of them. We only got 1 5. Let's take a look at this one. And, yeah, I have room. We've got the square root of 18a to the 4th. Well, we're going to do the numbers just like normal. Then we'll handle the variables a little bit differently. So I'll do my factor tree. 18 is divisible by 2, 2 times 9. And 9 is not divisible by 2, so I'll go to my next prime, which is 3. It is divisible by 3, 3 times 3. So, square root of 18, that's 2 times 3 times 3 times a to the 4th. Well, we're looking for a pair of somethings. Here's a pair of 3's. So a pair of 3's is going to come out in front as a single 3. And we got 3 square root of 2a to the 4th. Now I'm going to show you a shortcut when working with variables. I could write out a to the 4th, that's 4a's. And I could do the same type of thing. But if this was a to the 400, I wouldn't want to write out a 400 times. So let's look at our a's. You take your power, divide by your index, and this is old style division. 4 divided by 2 gives me 2 with a remainder of 0. So again, this is our power, and this is your index. Power is whatever power is in your variable. Index is whatever number's in the slot, and if it's a square root, it's by default 2. Now this tells us how many a's are going to come out, and then our second number here after the r tells us how many are going to stay in. So that tells us that we're going to bring 2 a's out, so we're going to have a squared out here. That 2 just carries in there. And we have 0 a's inside, so there's no a's left inside. So that'd be our answer right there. Start a new page, and we'll look at the next example. Oops. Number 9. We got the cube root of negative 52 p to the 6. Well, to begin with, we don't want this negative in here. We said earlier, if you have an odd index and you have a negative inside, you can just take that negative and put it on the outside. So I got negative cube root 52 p to the 6. I handle the p's here in a little bit, but let's look at the 52. If I do the factor tree, 52 is 2 times 26. 2's prime, so we circle it. 26 is divisible by 2. 2 times 13. 2's prime, so we circle it. And I guess here's one I didn't list. 13 is actually prime also. I guess some of them do go beyond just those 5 I listed, or 5 or 6. Okay. So I do negative cube root of 2 times 2 times 13 p to the 6. Now we did it in this problem just to see, but it doesn't benefit us any. Our index is 3. It means we're looking for a set of 3 of something. Well, we only have 2 2's and 1 13. We don't have 3 of anything. So number-wise, those don't come out at all. But let's look at the p's. We're going to take our power, which is 6, divide by our index. So again, our power on the P is right there, and then our index number in a slot goes right here. And this is old style division. 6 divided by 3 is 2 with a remainder of 0. Well, this is how many come out, and this is how many stay in. So negative stays out in front. We're going to have 2 P's come out. I'm going to go ahead and multiply these back through. 2 times 2 is 4, times 3 is 13, or times 13 gives us 52. And we said we have 0 P's remain in, so there's no P's inside the radical. And that's our answer. Let's take a look at this one. Got square root of 50 m squared into the third. Well, let's look at the number first, 50. Look at the factor tree. 50 is 2 times 25. 2 is prime, so we circle it. 25 is not divisible by 2, so I go to my next prime, 3. It's not divisible by 3, so I go to my next prime, 5. It is divisible by 5. 5 times 5. So this becomes 2 times 5 times 5 m squared into the third. Well, this is a square root. There's no number in the slot right here, so by default our index is 2, which tells us we're looking for a pair of somethings. Two of some, whatever. Well, here's 2 5s. So 2 5s are going to come out in front as a single 5. And then we got 2 m squared into the third. Well, let's look at how many m's we bring out and how many n's we bring out. Now for our m's, we'll take our power, which is 2, divide by the index, which is 2. Power, index is number in a slot, and if it's square root, it's by default 2. 2 divided by 2 is 1 with a remainder of 0. So we're going to have 1 m come out, and we'll have 0 m's stay inside. Pretty soon you'll get to the point where you do this in your head, but I won't do that for these examples. I'll write them over here on the side. Our n's, we'll take our power, which is 3, divide by our index, which is 2, gives us 1 with a remainder of 1. So this is how many n's come out, and this is how many n's stay in. So, let me see. We said we have 1 m come out. We said we have 1 n come out. 2. We have 0 m stay inside, but we have 1 n stay inside. So that'd be our answer. Let's look at this one. We got square root of x to the 13th. Well, let's figure out how many x's we're going to have come out. We're going to take our power, which is 13, divide by our index, and since it's square root, it's by default 2. 13 divided by 2 is 6 with a remainder of 1. So this tells us how many x's we have come out. This is how many x's are going to stay in. So we're going to have 6 x's come out, and we'll have 1 x stay inside. And that'd be our answer. One more of those. Got 7th root of x to the 23rd. Trying to figure out how many x's is going to come out. Take our power, which is 23, divide by our index, which is 7. Index is whatever number is in the slot right here. This is old style division. What was that 3 with a remainder of 2? This is how many come out. This is how many stay in. So we're going to have 3 x's come out. So we got x to the third, and the 7th root, and then we have 2 x's stay inside. So we got x squared inside the radical. And that's our answer.